Good morning, everyone. I'm going to talk to you a little bit about the rapid prototyping using micromilling, CNC high-precision micromilling, and 3D printing techniques. As Maggie has mentioned, both of these were widely used in our lab, mostly the high-precision micromilling as far as making microchannels. And so let's start. Okay. Let's start with this definition of two different manufacturing methods that apply not only to microfabrication, but to pretty much any fabrication you can come up with. And you can divide them. One of the ways to divide them is subtractive manufacturing, so-called top-down approach, where we start with the piece of material, and by slowly cutting it, milling it, chipping it out, we're coming out with the final let me move Joe a little bit away of the picture. Here you go. Coming up with the final 3D object. And what you could see in the lab, as far as we use in the scientific labs, right, in microfab, these methods would include traditional machining, milling, sewing, cutting, laser machining for cutting pieces, the wet or dry etching, focused ion beam milling. I believe we'll hear about this a little bit later as far as the as far as the nanofabrication efforts. Lithography can be also classified here. And the other way is the so-called additive manufacturing, when you start from the bottom and basically our 3D object comes from, I would say, nowhere, right? We have just pile of individual pieces of material and we assemble them to make a 3D object. And 3D printing will belong in this category as well as some deposition techniques. For example, you want to make a gold electrodes on the piece of plastic. You're starting with the gold atoms from either evaporation techniques or gold particles from sputtering that will assemble on the surface. The same works with electroplating. And again, some types of lithographies can fall into this category. So let's start with high precision micromilling. How does micromilling work? And I'm not sure how many of you have seen the milling machine in operation, but what we're using is a tool, it's a cutter that spins really quickly. And using this cutter, you can shape a piece of material. And for example, here is on the left cartoon shows the cutting of the cross versus here I'll show you the. Okay. A short video of the milling machine in action. So what we're doing, this fast spinning cutter, we're moving in XY direction into our material, and it removes the material, in this case, creating the channels directly into the pieces of plastic, right? And CNC machines can be as big as half of this room or as small as this desktop machine shown on the bottom picture, right? And similarly, depending what we're gonna cut, you can have milling bits that are half a meter in diameter, or you have a milling bit that's 50 micrometer in diameter, right? Depending on your needs and the okay. So to show you quickly how the manufacturing process works, we start with some kind of the design and CAD software, computer-assisted design. We then transfer it into the CAM software into the machine language that milling machine can understand, and it's really all user-friendly with mouse click approach. Then we can we can set up our milling machine, load our substrate, mill in our case, microfluidic channels, If we would like to mill more parts, we don't have to do any of those initial steps. We just load another piece and just keep repeating these two steps to make as many parts as we would like to. Let's see if I can. Okay. As I mentioned, milling beads come in different types and sizes, but ones that we typically use can go down to 25 micrometers. We mostly use something more in the range of 200 to 500 microns. And just to give you the perspective, this is all those pictures are kind of one and the same ratio as in comparison to human hair. So you can only imagine how tiny tools we're using in the process. To run those really, really tiny tools, that's this, in a sense, contradiction that to run really tiny tools, you need really big machines, right? The tiny desktop machine could never run successfully 25 micrometer bit because it's not stable enough, right? You need something really big, dedicated, like for example, this current Evo micromilling machine that we have in the KU Physics machine shop. It can spin those tiny bits up to 50,000 RPM with tools down to 25 micrometers, multi-axis machining, high aspect ratio of structures. And as you can see, those two positions, the positioning accuracy plus minus half a micrometer. This comes from the machine itself, which really gives you on the workpiece, correcting for all the environmental factors, about plus minus 2 micrometers. Now, what kind of applications you can have with milling and making microfluidics, making devices? And you can have two approaches. One is direct, right? And this is what you just seen on this very loud video, is where you're taking your milling bit and cut channels into the piece of plastic. And the other approach is that you actually cut a relief of the channel that you try to make. So you take a piece of metal, you machine around the structures in a sense that you want to become your microchannels, and then using replication techniques such as hot embossing, injection molding, and casting, you can make a relief of your structure in plastic. And you will hear more about the hot embossing, injection molding later during the course of this seminar. Few things to consider when we're using micromilling. And very often people ask, oh, so how small channels can you make? And the answer will be depending which method you would like to use. So if you can easily imagine that if you directly writing the channels, the smallest thing you can make will be whatever the smallest milling bit you can use, right? Then how deep it could go for the smallest bit is related to the aspect ratio of the bit. Typically, these are 3:1. So let's say if you were using 50 micrometer bit, you cannot make a channel that's deeper than 150 micrometers because that's how deep your milling bit would go, right? On the other hand, you can make those channels really densely because the spacing between the channels is only limited by the type of material and its characteristics. Versus if you go through the relief route, so you're trying to imprint something, it's a little bit different because you can leave the microstructure that's very thin. For example, you can use 500 micron bit to cut the walls that are 25 micrometers wide. And then once you imprint them in your plastic, you will get 25 micrometer wide channels, right? So it really depends on which approach you're taking. And we're successfully used both of those in our lab. I'll show you some examples. Another thing to consider is the shape. You're cutting pieces with the round cutter, right? So if you're trying to make a relief, any corner that you're getting into will have a radius of the cutter, right? And depending on the size of the cutter in relation to the size of your channels, this may be really visible. So instead of the cross on the left side, you could see the cross with clear rounded corners. However, if you finish these corners with much smaller bit, you can have something that looks like a perfect cross, right? Another thing to consider is sidewall roughness, right? The milling bits, as sharp as they can cut brass, aluminum, steel. There are some imperfections that in micro world may matter, right? You will never see it on some millimeter size parts, but you can see it in microchannels. So you can see that the cutting edge of the milling bit, its quality will be transferred to the sidewalls of your microchannel, or the sidewall of the relief that then will be transferred into the, if you're using replication technique, will be transferred into the channel itself. And this roughness also will be different in different parts, right? There will be different on the floor, different on the walls, and replication often also reduces the roughness as well. A few examples from our lab. So this is just a set of pictures of different possible structures. As I mentioned before, right, we were able to cut let's say the top row, middle. You will see the brass structures cut in brass that are 400 micrometer tall and only 20 micrometers wide, right? The only reason we were able to cut it is because it is a raised structure, right? The structure that then was used to replicate into the plastic. So whatever we left was only the material, everything around it was cut out, right? And that's the way how we can do high aspect ratio structures. What's also interesting was very, high attribute of micromilling is that you can do different height structures. It's very easy to step. So you have, let's say, like on those bottom pictures, you can have channels with the different heights done at the same time, right? In lithography, you would have to do two separate steps, two separate sets of masks alignment, versus here, you just cut it and you have this ability. Another example, and this is example that Dr. Sokol already showed on one of his slides. These were the microarrays for reading these were the PMMA chips for reading DNA microarrays with built-in prism for internal reflection of the laser light. And we could make it in the format. We could make it in the format that final chip could be put directly on the microarray spotter, as shown on this picture, the bottom picture, and we could just print arrays, then chop the chip, assemble it, and use it for readout of the DNA probes. We can also make different three-dimensional structures, such as interconnects, valves, and use it in the integrated microfluidic chips. I don't know how many of you ever had a chance to work with PDMS, for example. Persistent problem is that you use lithography to pattern photoresist on silicon wafer, of which you cast PDMS. However, very often, whatever you just pattern on the silicon wafer comes off with your first or second or third PDMS replication, right? So your master is ruined. You have to start from the beginning. Using micromilling, you can make masters that last forever. You can, for example, here, you can micromill the brass relief from which you make the copy in PMMA. They can also have all the posts for the access holes. And then you can fill it with PDMS, let it solidify. You peel off the design that has channels and access holes in one way. And we have also shown the use of this for patterning microarrays. Just to show how powerful it is for rapid prototyping. This is the example of this microfluidic microtiter plate before we finalize our design to move to really high resolution lithography and producing the nickel mold to do high quality replications. We wanted to check whether the entire fluidic structure works, whether this idea even works, right? So we would micromill this large area mold insert, hot embossed chips, you can see that due to the size limitation, what the technique is able to produce, right? Our posts were only 100 micrometers in diameter with large spacing, but we were able to make the plastic replicates like the one shown on the bottom here within 5 days from the design submitted to machine shop, machining, milling. And the longest time really that took was to making those tiny holes that ended up being posts. It's actually in the whole production process, it took 2 days of drilling, right? On this big red Kern milling machine. Now, the same process, once we saw, okay, fluidically it works, does what we want, we could move to design using the UV Liga, which is you first pattern photoresist and then you electroplate nickel, and then you use this nickel stamp to reproduce your plastic parts, and you can see that we could easily make a 10 micrometer post, right? But just having the confidence that what we do work was really big help, because we had to invest 5 weeks time of people that really knew what they're doing to get to this point, right? So just quick summary, some attributes of high precision micromillet. Nowadays, it's really fast and inexpensive, unless you want to push the limit, so you have to invest in $300,000 milling machine. But this desktop machine you can have for $2,000, and you can do a lot of microfluidics with it. 2 different ways to produce, with either direct write or replication. High aspect ratios. The walls are very vertical, as you could see on those on some of those SCM images. 2D and 3D components by using multi-levels or different tools to produce different features. And limitations, well, as I mentioned, just really limitations due to the size of the tool or the material properties, some wall roughness, and as compared, for example, to lithography techniques, and those rounded inner corners. Let's move on to the second part of the talk on 3D printing. So 3D printing, as I mentioned, is one of the additive manufacturing type of techniques. And I found this, I just copied, telling the truth, copied and pasted this definition, because it seemed really nice to me, because it's additive manufacturing process that creates physical object from a digital design, right? There is no mention of the material that you need to make this physical object. You just take the design and create the object, right? Which, yeah, we know it's not possible, but it really shows this definition shows the general approach that, or general status that 3D printing achieved over the last couple of years, that in many cases, it really is what this definition says. You have a design, 3D design, you take it to the machine that is 3D printing, you may know nothing about this. You just press the button and you get your part, right? That's how far 3D printing. It's not like with the milling, you may have to set up tools, you may have to set up your stock materials, right? None of that. There are ways to do 3D printing that you literally take a design, get the object, right? But in reality, yes, we're starting with some kind of feed material that we're shaping into the 3D object. And so what can 3D printing do? And well, it can really you can 3D print from meters to nanometers, right? So on the left one, you can see a 3D printed house in Germany made out of concrete. And on the right side, you can see the castle on the tip of the pencil, which is the total castle size is 230 by 250 by 360 micrometers, with the columns in sub-micrometer size, right? So it's a huge range of things it can do, and from meter to nanometers, and really anything and everything in between, right? From this stainless steel bridge in Netherlands through a hypercar, where chassis of the car was made of metal, by metal, 3D printing metal. The one on the right, I actually like it as the newest. SpaceX Raptor 3 engine is the third one, most on the right side. And you can see how much smaller it got just because some of the components took advantage of making by 3D printing, right? Could be made lighter, smaller. You can use it in sports for making the outsoles for the shoes, for example. That's no other technique could make the lattice like this easily and commercially viable. You can use it in healthcare. You can use it for hobby applications. And as I said, many, many more. So now, how is it possible that we have one technique that makes it all? And the reality is that it's really many, many different techniques. Each one of them has their own name that can take different feedstock material to produce objects. And this is the list. I don't even know if it's comprehensive, because it seems like many new companies that show up on the market, they change one thing in the ways they're doing and they put a new name. But there are few different major categories. Are fused deposition modeling. It's extruding really, really thin layers of strings of plastics and kind of joining them together once they're still molten. The other one is stereolithography, and that includes different. This way you can do stereolithography works on photosensitive resins, and some types are digital light processing, two-photon polymerization, and digital light synthesis. Polyjet is photosensitive resins as well, but you can do multicolor printing. It's really just like your laser jet printer in the office. The only thing is that it keeps printing, making, instead of just your text on the piece of paper, you can make three-dimensional features. Powder bed fusion techniques, it's when you spread a thin layer of material. So let's say it's a powder of a metal, and then you come with a laser and locally melt it, sinter the laser, the metal particles, spread another layer of the metal, follow up with the laser again, and in the end, you have a solid piece of the metal or polymer. There is wire arc additive manufacturing. This is how this stainless steel bridge that I showed earlier was made. Atomic diffusion, additive manufacturing, and bioprinting that's good for hydrogels, cells, and proteins. So now, some attributes. Let's move Joe around again. Well, actually, that would work. As I said, it's in some cases, it may be really, really simple process. You have your idea, you create the 3D design, you post-process it in the software, so-called slicer. It makes the program that's understandable by your machine. You feed it to the machine assembles the particles in a sense. Then you remove your parts. Very often there is post-processing involved, such as final curing of those photosensitive resins or a little bit polishing for the rougher parts. So it's very straightforward for the end user, right? In some cases, really, there is no prior experience required, but it still helps, as we will see in a minute. What you can do fabrication of what I call impossible parts, right? In a single step. So if you look at least this, there is a ball with holes, inside a ball with holes, inside another ball with holes, right? If you were trying to do more conventional ways, you would have to probably produce half balls and then 3 of them and then assemble everything, right? Versus in 3D printing, you can do it, right? You can create object within the object within another object, right? There is no retooling necessary for parts that they may need otherwise different tooling. And there is example here of 3D printing. This was the, I believe, ion extractor that if you can see, this is the design. You have a piece of polymer that has microfluidic channels. There are two extractors here that are formed by the lattice of those polymer cubes. And there is also threaded inserts, so you can put those upstitch fittings to it directly, right? And all it is done in one step. If you try to do it by machining again, you would have to start multiple pieces. You would have to retool to thread the holes, and etc. When you're trying to do small batches, the machine may be the technique may be really fast when we're talking compared to, let's say, conventional machining. When you're talking kind of the finished product, right? Of course, machining is still can be also very fast in some cases. We can nowadays, since the technique has been with us for a while, for the last 40 years, you will have wide selection of materials to choose for. That's why you can print polymers, metals, ceramics, but it's still considered relatively young, right? So you still have improvements going on, and they are related both to speed, cost, and how user-friendly they are. So I just showed this table from one of the review papers. And I'm only gonna talk about stereolithography more today, but you can see out of those different techniques, you're gonna get this presentation. So if you're interested, just look through it. And there are also a lot of reviews out there to compare different of them and how useful they are really in the producing parts that you can use in the laboratory, right? So let's just move on to stereolithography. On the cartoon on the left, you can see the basic idea how it works. There is a container with photosensitive resin, which means once you hit it with light, it will solidify. And there is a stage on which you're building your part, right? And in the original setup, you would have a scanner with the laser or the UV light slowly scanning the surface and building line by line, layer by layer, solidifying this resin so you can get your final 3D object. And as top layer was exposed, you finish exposing one layer at the top, you move this Z stage lower, you expose. So you can see similarities with the milling in a sense. In the milling, you had this spinning cutter going and moving at X, Y, Z, cutting the pieces, versus here, you're building your object in a sense in X, Y, Z directions, right? And this is the oldest 3D printing technique that was first conceptualized and demonstrated actually with few patents filed in 70s and early 80s. But the person Chuck Hull is recognized as a father of 3D printing because he was the first one that actually demonstrate practical use of it, and it showed that it can be really used broadly in the industry. And there is a picture of his original patent for the system. And actually, in 2016, I believe, yes, the first 3D printer, SLA1, produced by 3D System, was recognized as the historical mechanical engineering landmark by the American Society of Mechanical Engineers. It shows you how much importance people recognize 3D printing, of how much importance it is for the industry, right? So over the years, there was a lot of improvements how 3D printing could be done. So instead of having laser coming from the top, now more often we have the laser coming from the bottom, with the bottom of our container being transparent. And as we're building the part, it actually comes out, the part is moved out of the resin solution. Improvements were made into, instead of using laser and scanning, just like here, if you would like to make this wiggly line, you scan the laser piece by piece. The more popular now are projection techniques, where the image of your squiggly line estimated here, is broken into small pixels, just like you have pixels on the monitors or pixels on your screen with certain resolution. And this image is projected on the resin. It solidifies, the stage moves up, new resin flows in, you project new image corresponding to this layer, and as it goes, it just builds 3D images. Instead of line by line, it does it kind of plane by plane. Just to show you how important those instrumental developments were, the original SLA1 stereolithography printer costed about $300,000 in 1986, and I believe it wasn't inflation adjusted for now. You can buy 3D printing on Amazon now. That pretty much the idea is the same, right? For $150 now. So that's how improvements and well, that's how actually, how they call it, democratization of the technique happened, right? So everybody can do it. Now, let's talk a little bit of things that we're interested when you're doing micro features. It's what's the resolution of the technique, right? And you can easily see as the resolution in our milling parts were dependent on which format we chose and ultimately the milling bit size. Here, the resolution is primarily defined by our spot of the laser, if we're doing typical SLA, or if we're using projections, would be how big those pixels are, right? Because that will ultimately, these are our tools. That's how the resin hardens in its volume, right? And another thing is step resolution in Z. So what's the resolution between those layers, right? As we're making our parts, it moves layer by layer. So what's the thickness of the layer, which directly is related to the movement in Z? And as we'll see in a second, it's also what's important is, okay, what are the processing conditions? For example, how much radiation we put, what's the radiation dose onto the resin or resin components and physical properties. And anyway, for the example I choose here from the literature to demonstrate how powerful technique it might be is this 3D printing of this gradient generator for different solutions. And you can see it's a chip that mixes different, on this picture, mixes just different colorful dyes, right? And makes a constant gradient in the end. And it uses the different mixers that try to overcome the limitations of the Reynolds numbers that Dr. Soper mentioned earlier in mixing on microfluidics. But what's important is that this whole chip was done in one run, including microchannels, including the connectors at the top, right? Different sizes, different functions built in one piece in a single process, right? And as we're talking about the resolution, we look at the specific commercial 3D printer was DLP type with the pixel size relatively large, 56 by 56 micrometers, and Z-step height of 50 microns. So you would assume that making channels on this order of magnitude would be, okay, that's what mechanically possible, right? But when these researchers did their studies, the smallest channel that was still open after the processing was actually on the order of 250 microns, right? So much larger than what theoretically possible with this equipment. And there was an interesting survey done by another group that looked at different 3D printers, the results of 3D printed but different groups, and compared, put in a single graph, so what this technique was claimed to be as a resolution versus what you really could get in your final product. And as you can see, for all this array of different SLA, PolyJets, or FDM type of printers, none of them really delivered what you would think would be possible just looking at the spec sheet, right? And it all comes from the type of resin used, to the viscosity of the resin, what the dose is, right? All these studies use the standard protocol. So use those printers in the way, as I mentioned before, that you just make your design, come to the printer, press the button, and you get your part, right? So sometimes the difference was 1 order, sometimes 2 orders of magnitude, right? So what does it really take to do real microfluidic channels? Microfluidic channels that are below 100 microns, right? And the answer is it takes a lot of elbow grease. Sorry. So this group at Brigham Young University, they built their own printer with DLP resolution down to 7.6 times 7.6 micron. With this D-step resolution, 5 micrometers, right? They also included in their setups, they have dose calibration, so they can choose for specific resins, they can actually calibrate what dose they want to use to achieve the perfect results that they're after, right? They tested multiple resin formulations. They looked through 20 different absorbers till they come up with one that was giving the best results, right? And optimize the process. You can see here size of the channels, different channel sizes depending on what's your step resolution. You can see when they step, so each layer thickness was 5 microns. You can see relatively nice and smooth walls over entire channel, but you increase it to 10 micrometers to build 30 micron channel. You can clearly see each layer in the channel, right? After all these optimizations, they were able to demonstrate, for example, a serpentine channel with this 18 by, I think 25 by 18 micrometer channels and multiple different layers. So think about this. If you were trying to make a design like this by milling, you would have to make each one of those layers separately and then put them all together. Right here, you can print it in one shot. You could also, they were able to do really, really high aspect ratio structures over 130, right? So the channel was 3 millimeter tall and somewhere 12 microns at the bottom and 23 at the top. And you can actually see all those individual layers. So as I mentioned earlier, looking at the attributes of 3D printing, yes, it is possible to use this definition that you have just idea, digitize it, print it, and you get your part. But if you really want to push the limit, it still takes a lot of research and development, right? And so the last type of the SLA that I thought it's worth discussing is this stereolithography in the nanometer regime. It uses this so-called 2-photon polymerization and comes from the fact that if you're using just what we see in previous examples, it's 1 photon. You really polymerize a lot of resin. Anything, even if you focus your laser or your UV light, polymerization will occur at the relatively large volume. So you have certain material, a larger volume of material that's being polymerized on one side. If you use 2 photon based on with the lasers, with fast lasers, you really make sure that the intensity, its maximum intensity is achieved only at the focal plane, because it's based on probability that you need to at least 2 photons to polymerize your polymer. And it is your resin, right? And it is probability, basically. So what you can do with this technique, and you can see here, you can build really tiny features actually inside of microfluidic channels. An example here is a little nozzle for producing polymer strings inside the channel. So the size mark here is 50 micrometers. So you can see how tiny it is. And this is another example of the mixer with the walls on the order, I believe, of 2 micrometers built inside of the fluidic channel. The resolution, the minimum resolution, so voxel size, I forgot to mention it. Voxel is a pixel in 3D printer, right? Everybody knows pixels from the scribble resolution or printer resolution, but pixel is 2D, so it's just a little square, right? Voxel is volumetric pixel. So it's really 3D. So the smallest volume of your 3D built part. And here we can go down to, with 2-photon polymerization, we can go down to 100 nanometers to 500 nanometers lateral and 100 to 1 nanometers to 1.5 micrometer axial in sizes. And I believe that's it. I don't know if we have time for questions, but if we don't, we do.
I'll walk with the microphone to you if you have questions. Can you comment on actually 3D printing and high throughput and mass scale production? It does look a little bit.
So
there are some discrepancies that I see. Can you comment on that?
Discrepancies.
Well, I don't know if you can mass produce using 3D printing.
So let's put it this way. If we look at for example, this ball, this was actually done with the multi-jet. So let's go quickly. Okay. So this one, multi-jet fusion printing. So the technique works, all those powder bed fusions I mentioned, what you can do, you run, you have a big, say, container with the particles, right? For example, this was polymer, right? A layer of polymer particles. You bring the laser that melts the plastic to one layer of your part, right? What you do then, you feed another layer of the polymer particles, you spread it evenly on the top, and the laser comes again and really quickly produces those parts. And it goes layer by layer by layer. Machines that do it on the actually HP, that's interesting since they invented the laser printing, right? HP actually makes one of the biggest industrial printers that do this way. And according to what they say, those parts rival injection molding parts as far as the speed and cost. Because the only thing, if you think about this, so let's put it this way. I can't, because I don't necessarily agree with this, but I don't know, I cannot probably. In this original picture, if you look those cartoons online, it will show you there is another position here that you start with material, you cut it out, and you produce a lot of waste, right? Because everything that you cut out becomes waste. When you do 3D printing, you only assemble it, so there's barely any waste, right? There are some issues with that I didn't discuss it. So the advantage of, for example, 3D printing in the mass scale, when you have this big bed of the particle polymer that you're just sintering to create your 3D object, is that you can reuse everything that wasn't sintered, can be feed back into, and you keep reusing this, right? So you're saving a lot of the material cost in this sense, right? And you don't have any tooling, as Dr. Park will show. The injection molding and hot embossing requires tooling. So you have to start first with making a tool so you can make your part. And this can run you in hundreds of thousands of dollars, right? But with 3D printing, you just press the button.
Thank you. Questions? Oh, I'm sorry. Well, Ryan, you need to come closer.
Ryan, come down.
Thank you. You asked about mass production with 3D printing, and I'm sorry, I don't know specific models, but my understanding is that there are some stereolithographic tools that can produce parts quite rapidly that could qualify as mass production tools. So, well.
We're going to move on to the next presentation.